Yes, so thanks a lot, and thanks a lot for having me for this seminar. So I would like to mention this is joint work with Bill Rundell from Texas A&M University. And as was announced, it will be about the coefficient identification problem. And it's in the context of fractional PDEs as follows. So it starts off with something which is non-fractional. So that's a very classical problem. We have an elliptic equation, second order elliptic equation, with an unknown coefficient q of x and a very simple geometry. So the geometry can be made more complicated, of course, but for illustration, we are just looking at this type of setup. So we have a coefficient that changes in x direction. So one could imagine this is stratified medium. So in this direction here, and then so things change in x direction, but they remain constant in y direction. Especially this q of x is constant in y direction. Of course, u depends on x and y, and it satisfies this PDE. So this minus Laplace is uxx minus uxx minus uyy. We have Dirichlet boundary conditions. So for simplicity, on these two boundary parts, they are just simply zero. On the other parts, the boundary conditions are given functions phi 0 and phi 1 of y. And then you see we have an additional boundary condition on this part of the boundary here. The inverse problems that we are studying is to recover this potential, the q of x, from this overposed data g of y. So it's basically trading two functions against each other. So this one is given, g of y. The model is given, but we want to find the q of x. And also typically one only has noisy data. So g delta is a noisy version of the flux at the left-hand boundary point. So now we would like to move into a fractional, space fractional setting where instead of the Laplace operator from the previous slide, we have a fractional operator, L alpha. So alpha is the order of differentiation that appears here, which might be something between 0 and 2, or actually it will be between 1 and 2, so that it still is mimicking the Laplace situation. But of course, there's also the q of x still appearing. This is still our searched for coefficient. And instead of minus uxx minus uyy from the previous slide, we have some fractional derivative in x direction, or we have a fractional derivative in y direction, where alpha might be somewhere between 1 and 2. So the classical case from the previous slide would just be alpha equal to 2 in this setting or in this setting. Still, the inverse problem is to given all these boundary functions plus the boundary flux, or maybe a noisy version of the boundary flux, we want to recover q of x. Just to explain what these fractional derivatives are. So these are, first of all, these are defined via fractional integrals. And these fractional integrals are these Abel integral operators. So this, such an Abel integral of order gamma, with gamma between 0 and 1, is defined by an integral that is, so to speak, counteracted by such a singularity in the integrand. So we look at a convolution between v and this weakly singular function s to the 1 minus gamma in the denominator. In the case gamma equal to 0, then this is, at least it converges to just basically the delta function, so it becomes v itself. And so the integral operator corresponds to the delta distribution. In case gamma equal to 1, it's just, so this thing here goes away, and it's just once integration. It makes a difference here from which side we start, whether we start with the left-hand boundary part with our integral. Likewise, one could also start at x and go to the right-hand boundary part, and this makes a difference also for the inverse problem, as we will see. So starting from these fractional integral operators, we can define fractional differential operators by just combining one of these one-sided integral operators by an integer with an integer differential operator, so that alpha derivative that appeared in the PDE on the previous slide, that's defined, for example, by just taking the second order integer derivative and, so to speak, removing 2 minus alpha derivatives, so that we end up with an alpha derivative. So that's the Chiapascian-Caputo derivative. So there's also the Riemann-Liouville derivative, where one first does the integration and afterwards the differentiation. But the advantage of this DC derivative here is that one can, it corresponds to very well to, in the context of PDEs, to prescribing integer order boundary conditions. So for example, this second order derivative goes well with prescribing the 0 and the first order derivative as boundary points, which is not the case for the Riemann-Liouville one. We will also look at a two-sided version, and actually a symmetric version, which is of Riemann-Liouville type, in the sense that we first integrate and then differentiate. The way we have posed the boundary conditions to be 0, this is still compatible. And so what we do is this symmetric type of doing both types of Abel integral operators and then doing the second derivative. So it's an easy computation to find out that yes, this as it's called Ries derivative is symmetric with respect to the L2 inner product. So this is a symmetric differential operator. Of course, this has certain advantages, because for symmetric operators, one can do at least a bit of spectral theory, and that's actually something which we are going to need later on. Before going to a bit of theory, namely about uniqueness, let's have a look at reconstructions. So let me mention that trying to recover Q of X from in one of these PDEs from this overposed data, that's a nonlinear inverse problem. And so, although the forward problem is linear, but linear with respect to the solution, but bilinear, so to speak, with respect to Q and U. And from this, it results in a nonlinear inverse problem. So we have to apply some solution method for nonlinear problems, and it's actually Newton's method that we are applying here. So in order to assess the degree of ill-postedness of a problem, a suitable way is to look at the linearization. So just to look at one of the Newton steps and then compute the singular value decomposition of the Jacobian. This quantifies the decay actually of these singular values, quantifies the degree of ill-postedness. So let's have a look at the singular values. For example, in case of the DC derivative in x direction. What I would like to illustrate here is that this degree of ill-postedness, so the speed with which these singular values decay, depends on the order of differentiation. So the fastest decay, and therefore the strongest ill-postedness, which is the worst case, appears in the classical setting when we have a second derivative in x direction. And as you see here, if we take a lower derivative in x direction, this mitigates the ill-postedness. That's an effect that has been observed also in the context of for another classically inverse problem, linear one, backwards heat equation, where one can see that actually going from an integer derivative to a lower order derivative, one can achieve that the problem that is originally exponentially ill-posed, that this becomes mildly ill-posed. So taking fractional derivatives can be also viewed as a means of regularizing, so making the problem less ill-posed. And to some extent, it also takes effect here. As you can see here, there's also a difference between taking the observations at the left boundary versus taking them at the right boundary. So you see the problem is slightly better because the singular values decay, especially if alpha is smaller than 2, the singular values decay slower if we have measurements on the right boundary. Why is this so? Maybe let me explain this back with this picture. So we are looking at this situation where we have the DC derivative starting, as it's not visible here, but we have a DC derivative starting at 0. So it's a derivative that uses an integral that goes from 0 to some x. And if we go all through the right-hand boundary and take measurements there, it takes derivatives that, so to speak, by their non-locality due to the integral, have a memory that really goes from left to right. So if now we take our measurements not on the left-hand endpoint, but on the right-hand endpoint, that's the situation that we consider with the slower decaying singular values. If we take them at the right-hand endpoint, then the memory that is hidden inside this derivative, the memory stretches from that 0 point up to the right-hand endpoint. And it provides us with information that spans the whole range. Yes, so this non-locality is, so to say, it's a memory that goes from 0 to this right-hand endpoint where we take our measurements. And that's why it's better to take the measurements at the right-hand endpoint, because it makes use of the memory from left to right. That's the explanation for this slower decaying singular values, so for the better, so less ill-posedness of the problem, as compared to the situation where we take measurements at the left-hand endpoint, where the memory does not is not of so much use, to put it like this. This can also be seen in the reconstruction. So also here we consider the DC derivative in x direction starting at the left-hand endpoint. And again, this is the situation where we also measure at the left-hand endpoint, whereas here we measure at the right-hand endpoint. So the upper row is with 0 noise, the lower row is with 0.1% noise. Since it's an exponentially ill-posed problem, we can only take a small amount of noise, so 1 per mil, and you already see that the reconstructions deteriorate. What you can also see that in these reconstructions from noisy data, so this one here, the right-hand picture, is slightly better than the left-hand picture. This is on one hand due to this memory effect, because measuring at the right endpoint makes really full use of the memory of that non-local fractional derivative. So you get a better fit over here. But also there's another effect that is visible here and that will persist also in the symmetric case, namely that here we have sort of a dominant feature, so a stronger contrast on this side in our Q. So what you see here is the Q, the black line is the exact Q of X, and the green and red lines are the reconstructions. So Q has a higher contrast over here as compared to this one here. So if we measure on the right-hand side, then the left-hand feature is, so to say, in the shadow of this right-hand feature, and it can be less well reconstructed. And this is visible actually in all these pictures. Whereas here, if we measure at the left-hand endpoint, also down here, in some cases, this shadowing effect will be a bit less pronounced. So this was reconstructions with the DC derivative in x direction starting at 0. So starting at 0 in all these cases, but measuring at the right-hand endpoint here for the red lines, and measuring at the left-hand endpoint for the red lines, so here, and measuring at the right-hand endpoint for the green lines. Okay, now we take a symmetric derivative, still fractional in x direction, so the same direction where q of x depends. But what you see here, the difference between the left and right picture now really comes exclusively from where we measure. So we can always measure the feature, reconstruct the feature better that is closer to our measurement point. So here we measure at the right-hand endpoint, and so we can recover this feature better. Here we measure at the left-hand endpoint, so we get a better reconstruction of this feature over here. So the memory effect does not make a difference here because the raised derivative is symmetric. It combines memory from both endpoints. So these are reconstructions with noise, 0.1% noise. So now we move on to a derivative in y direction. And actually, basically, like in the symmetric case, now it should not make a difference. So the memory effect should not make a difference because actually in x direction, we don't have a memory. In x direction, we have an integer derivative. Only in y direction, so perpendicular to this, we have a fractional derivative. So what we observe here is that in general, with measuring on the left at the left-hand endpoint, we get completely worse reconstruction as compared to this one. And that's, so our explanation for this was that maybe here in this situation, well, that's maybe just a random effect. So here we actually measured more closely to this one, and nevertheless we got worse reconstructions here. This was actually the other way around. Okay. So in this situation, in this symmetric situation, so to say, randomness is dominant. So again, we have a raised derivative in both directions. And what we can see is sort of a regularizing effect. So the ill-postedness is less pronounced. So also here the ill-postedness is stronger than in the previous pictures because we have an integer second order derivative in x direction, which makes things worse. Whereas here also in x direction, we have a fractional derivative. So this xy means that we have a fractional derivative both in x direction and in y direction. Okay, now about a bit of theory, namely uniqueness. What one can prove here is that if we have a DC, or also if we have a raised fractional derivative in y direction, so in vertical direction, then we can uniquely recover q of x. So you see that's the PDE that we are considering here. Here's our q of x. And the derivative in y direction is fractional, whereas the derivative in x direction is just second order classical integer. So the observations that we have are boundary observations on all the boundaries. So directly on the left and right hand boundary. And then this is a slight generalization to the pure Dirichlet conditions on top and bottom that we previously had. So we also can admit impedance boundary conditions here. The overposed data is this one here. That's the boundary flux. Again, now we are concentrating on the boundary flux at the left-hand endpoint. So we would like to show that for properly chosen excitation A, so the excitation of the system is just via this boundary condition here. Everything else is 0, so right-hand side of the PDE, and also the boundary conditions, all the other boundary conditions are homogeneous. So excitation is via this A of x function. If we do this properly, then we can uniquely recover q of x from this overposed data g of y. And that's due to the fact that we are now considering, we are doing a separation of variables. That's the plan. So we consider an eigensystem of this purely space part here. So that's the second order x derivative. So this purely x derivative part I wanted to say. So we have a second x derivative here. And also here the space dependent comes into play via the space dependence of the potential. So that's, so to speak, the space variation differential operator part. And of course, that's a second order elliptic one-dimensional differential operator. It's equipped with exactly these impedance boundary condition. And this has an eigensystem. So a lot is known about these eigensystems of the eigenvalues and eigenfunctions. So if Q is non-negative, then also these eigenvalues, mu j and will be non-negative. And also the psi j's have nice properties. In particular, they are incomplete in L2. And we can use this eigensystem, which is unknown. So because we don't know Q, so also this eigensystem is unknown, but still it exists. So we can theoretically use it to expand the solution of this boundary value problem up there, to expand it in terms of these eigenfunctions. And it can be easily seen that this expansion contains, contains the coefficient of this excitation function here. It also contains the eigenfunctions clearly. So the x dependence is governed by the eigenfunctions, by this eigensystem here. And the y dependence is governed by functions wj. So doing separation of variables, we find out that these wj functions have to satisfy clearly, so to speak, the y-dependent part of the PDE. So if we look up there, it's this fractional alpha dc derivative, or it could also be a raised derivative. So this fractional derivative acting in y direction that now acts on our wj ansatz functions. And in place of this minus xx plus q part, so this differential operator in x direction, since we have done the expansion in terms of the eigenfunctions, this is just replaced by the mu j, by the eigenvalues. Okay, that's the ODE, yes, the ODE that has to be satisfied by the wj functions. With boundary conditions. So first of all, in order to get these homogeneous boundary conditions, we have a homogeneous boundary conditions at the left-hand endpoint. And in order to recover the non-zero Dirichlet boundary condition, we normalize these wj's to satisfy 1. So afterwards multiplying with the coefficient of A, this gives us back this boundary condition. So this ansatz already takes into account this space differential operator and also the boundary conditions here. And by using solutions of this boundary value problem, we also take into account, so to speak, the y direction part. Okay, assuming that we can solve this, and actually it's possible to solve this, we can use those of you who are maybe familiar with fractional differential equations. There exists also Green's functions for such 2-point boundary value problems, also for this fractional case. But we don't actually explicitly need to use this, solve this. We just need to know that these things have a solution. And actually one can show that these solutions are linearly independent. So for different j's, the family of solutions to this 2-point boundary value, to this fractional 2-point boundary value problem, gives rise to a linearly independent family of wj's. That's something that we are going to use in a moment. So this way we can represent the solution of the boundary value problem. So from the first 3 lines up here. And now we would like to express the actually observed data by means of this. So we have U basically. now we would like to write the data. So we have to take the x derivative of our u. X derivative means that we have to take psi j prime and evaluate at 0, x equal to 0 here. That's why we get a psi j prime of 0 over here. So this is g of y. Just plugging in u of x, y, this formula up here. We can actually get more information on g because we can differentiate in tangential direction. If we take actually a fractional derivative of g, the alpha fractional derivative of g in y direction, we can plug in the thing into the PDE. So the alpha y derivative of g has to be compatible with the PDE in the sense that it has to be equal to the alpha derivative of u in y direction, which by the PDE is equal to u xx minus q of xu. But u xx minus q of xu, if you expand it in terms of the eigenfunctions, then it means that we are applying this x direction differential operator, and applying this to eigenfunctions results in multiplication of the eigenfunction with the eigenvalue. That's why taking this alpha derivative of g is and results in this expression here with a minus, because we have put things to the other side. And that's the mu j popping up because, okay, taking this alpha derivative amounts to applying this x direction derivative whose eigenvalues are the mu j's. That's why we get an vector mu j here. So what I would like to show you with this is that taking these boundary measurements, g, and also maybe a derivative of g, for example, by doing numerical differentiation of our data, we get quite a bit of spectral information. We get something which involves the derivative of the eigenfunctions on the boundary here and here, and it also involves the eigenvalues. But these eigenvalues and eigenfunctions are still hidden inside a sum. Yes, we have an infinite linear combination of these eigenvalues and eigenfunctions. But they are also come with a y-dependent function wj. In both cases, they come with these y-dependent functions wj. And as I mentioned, these wj's are linearly independent. That's an important piece of information because, for example, if g is 0, if g vanishes identically due to linear independence of wj, and since we will choose our excitations such that all these HAs don't vanish, what we would end up with is that all these boundary fluxes of the eigenfunctions would have to vanish because of the linear independence. However, proving uniqueness does not only amount to showing that if the data vanishes, then also our solution vanishes, because we have a nonlinear problem. So what we really want to show is that if we have this data, so g and also its alpha derivative, then we actually can recover the whole spectral information. From that spectral information, we are going to recover the potential. First of all, to really disentangle the spectral information, namely boundary values of the eigenfunctions and the eigenvalues, we are going to apply a dual basis because, well, the wj's are linearly independent, and as soon as we have linear independent functions, according to the Hahn-Banach theorem, that's just one of the conclusions of the many conclusions of Hahn-Banach, there exists a dual basis, meaning that in this case we are in the dual space of L2, which is again L2. There exist L2 functions such that we apply them. We can single out the single components in that sum. So due to this orthogonality property of this dual basis with respect to our W's, applying now Wj to the whole sum singles out the jth component here because of the orthogonality. Okay. So what we get from this sum is just the jth component here, aj times psi j prime at 0. And doing the same over here, we get minus aj mu j times, so this one becomes 0 or 1, and just 1 if at our j, where we apply our wj star. So it's again psi j prime at 0, but multiplied with mu j. So you see this down here, which we can also write as mu j times our 0 order information, so the information that we can directly obtain from the data. So from this, we get, first of all, the psi j prime of 0 for all j, and also the mu j for all j. So provided that all the aj's are non-zero. And for this purpose, let's recall that aj's are the Fourier components with respect to the basis psi j of our excitation. So for example, for simplicity, if our excitation is just delta 0, then all its Fourier components, even without knowing these eigen functions, so all these components of A have to be non-zero. Because in that case, if A is, oh no, not AJ, sorry, this is a misprint. A itself should be delta 0. So if A itself is delta 0, then this means we just evaluate our eigenfunctions at 0. And this cannot be 0 because the eigenfunctions satisfy homogeneous impedance boundary conditions. And then this would mean that both Dirichlet and Neumann conditions would be 0. This cannot be because then the eigenfunction itself would be 0. But by definition, an eigenfunction is non-zero. Okay, so there exists an excitation, and there might be others, such that all these coefficients are non-zero, and then we can really extract all the spectral information, namely boundary value of the flux and eigenvalues of our eigenvalues and functions of this operator here. And now what we are going to apply is Sturm-Liouville theory. Sturm-Liouville theory is a really nice machinery that allows to conclude from having spectral information to information of coefficients of the underlying differential operator. And particular this piece of information, namely having a sequence of eigenvalues and corresponding overposed data, so to speak, of the eigenfunctions. So we don't know the whole eigenfunction, but we know its flux at one boundary point. In this nice book by Pöschl and Trubowitz, one can find a result that tells us from this we can find Q of x. Okay, so if we have operators minus second x derivative plus q1 and the same with q2, and these give the same eigenvalues and eigenfunction boundary values, then the potential have to coincide. And since we have seen that from all the information that we have, namely the overposed boundary data, we can really extract that spectral information. It also tells us that we can uniquely recover Q of x. So the boundary data G, first of all, as an intermediate step, gives us the spectral information. And then as a second step, it gives us really the coefficient that we want to have. Okay, now we would like to see, so we get uniqueness if we take the dc or Ries fractional derivative in y direction. Now we would like to see whether the same thing holds if we take fractional derivatives in x direction, so in the same direction as we have dependence of the q. The answer is unfortunately no. And the reason for this is that there's really a missing piece in the spectral theory. So Sturm-Liouville theory is very well developed for this integer derivative case, and here we actually deal with the integer derivative in x direction. But if as soon as we go for a fractional derivative in x direction, there's not so much known. And in particular, this nice result that allows to uniquely recover a potential from this particular spectral information is not available, as at least as not as far as we are aware of, if we do a fractional derivative instead of this integer second order derivative. Still, one can move to a certain extent, and let's now just do the steps, the analogous steps, with an y fractional derivative replaced by an x fractional derivative. So here's the boundary value problem that we are considering. So the forward problem would be that given q of x, we want to solve this fractional elliptic boundary value problem. So we have an x fractional derivative now. We have Dirichlet boundary conditions. And so the first two lines are the elliptic boundary value problem. Additionally, we impose flux data again at the left-hand boundary, and we would like to recover q of x from this additional information. Now we do the same step as in the previous uniqueness proof. Now we restrict ourselves to a fractional derivative in x direction because we want to do a separation of variables, and for this purpose we would like to have existence of eigenfunctions, namely a complete set of eigenfunctions and eigenvalues for this operator here. And it's again the x operator, so the x direction operator, which is now fractional differentiation order, and still it's the q of x multiplication. And the boundary conditions are, for simplicity, just homogeneous Dirichlet. So this is a self-adjoint operator with a compact inverse. So according to the spectral theorem, we have a spectral decomposition, we have completeness of eigenfunctions. Again, the eigenfunctions are unknown because we don't know the q. So still we denote the unknown eigensystem by a sequence. So mu j are again the eigenvalues, psi j are the eigenfunctions. And we can expand in principle, because of this completeness here, we can expand our unknown solution u up here in terms of these x-dependent eigen functions in x direction times some functions w in y direction. Again, multiplied with these factors aj, where the aj's are the components of this excitation function here that we apply at the right-hand endpoint in x direction. Okay, and now this time, clearly, since we do a separation of variables, w is the y-dependent function, so it has to capture this second integer derivative in y direction. So that's this just second ordinary derivative. And what remains is again the space derivative part, which is replaced by, since we apply it to eigenfunctions, it's replaced by just multiplying with the eigenvalue. So that's why we get a mu j. So this space derivative, so d alpha x plus q becomes just a factor mu j here. And also the boundary conditions should match the boundary conditions that we have here in, that we have in y direction. Yes, these boundary conditions here. Okay. So now, again, we can expand the solution like this. And as a consequence, we can write the g of y by just plugging, first of all, taking x derivative, plugging x equal to 0. This gives the same formula as before, just with w and psi having a slightly different meaning now. We can also, again, differentiate our data in tangential direction. That's possible, for example, numerically. This time, we want to take this y derivative, so it's just a double prime here in y direction. And again, due to the fact that we can express this via the PDE as, again, our space derivative operator, or actually minus the space derivative operator applied to u, we end up with a factor mu j, again the eigenvalue, actually minus mu j, because we have put it on the other side. And again, clearly, this gives us spectral information. It gives us also, these are linearly independent function, and actually one can write them explicitly. Yes, we can explicitly solve this boundary value problem. So we don't have to say theoretically they are linearly independent. We can write them down, and yes, these are linear independent functions. So we can play the same game as before. So use these dual bases in order to disentangle both sums. So degenerate them to single summands. So this is done by applying the basis to this function of y and applying the basis to this function of y. Again, we get the flux of the eigenfunction, of the unknown eigenfunction, and also the eigenvalue, and we get this for every j. So again, we get a sequence of eigenvalues and also boundary values. So if Sturm-Liouville, inverse Sturm-Liouville theory would be available for this fractional differential operator here, then we would end up really with a uniqueness result. But unfortunately, it's not yet the case, and that's why I would really like to pose this as an open problem. Maybe one of you wants to take a closer look into this and solve it. This would be a really nice result, and please let me know if you have solved it. Okay, now how much time do I still have? So it's almost, it's now 43 minutes. Maybe I should
45 minutes. You have just 5 or 6 minutes for the talk, and then we will have
okay. Okay, great. Thanks a lot. Then maybe I can say just one more thing. Well, it's really nice that we have all this spectral information. Unfortunately, we really cannot guarantee that Q is uniquely determined from this, because we don't have this inverse Sturm-Liouville theory. However, there's still one piece of information that we can recover, and that is also of interest, namely this fractional order alpha. And actually, it's even too much information that we have. We can recover, as we will see in a moment, this fractional order alpha, which is just one number, from just looking at the asymptotics of the eigenvalues. Because for the asymptotics of these eigenvalues, well, we don't know the eigenvalues, but we know that if Q is an L-infinity function, the asymptotics of these eigenvalues are basically j pi over 2 to the power of alpha. So actually this power up here is reflected in these eigenvalues up to some error that is a lower order. So actually this is something which goes to infinity as j tends to infinity, and both these terms are bounded as j tends to infinity. So actually this is really the dominant term in the expansion of this eigenvalue. And so on the other hand, taking the log, clearly because we want to have the exponent, taking the log of the mu n and dividing by the log of this one just gives our alpha, at least in the limit as j tends to infinity. So actually what we really need is not all these values, but just its asymptotics. How fast do they decay, how fast do they increase, of course, as j tends to infinity. Okay, now maybe let's just, since we have been using these solutions of these fractional PDEs, if one can do this separation of variables, of course, one can also show under certain conditions on the boundary values that solutions exist. If one wants to do Newton's method, actually one needs a little bit more, because then one will also have to solve such boundary value problems with a non-zero right-hand side, which basically comes from linearization. So what we also looked at is well-postness of these problems. So these are different types of PDEs that we considered here, depending on whether we take x fractional derivatives or y fractional derivatives. Actually, in case of x fractional derivatives, we can be a bit more general in y direction. So we could go to higher space dimensions in y directions even, and generalize the Laplace operator that we had there in one y dimension to a higher dimensional Laplace operator. So this is just to illustrate that really for studying these boundary value problems, the proper spaces are Bochner spaces. So you probably know Bochner spaces from the context of time-dependent PDEs, where time plays a particular role. So we have a certain differentiability in time derivative with respect to an x-dependent space. Now, here x is clearly x is the component that plays the particular role, like time in evolutionary PDEs. And actually the solution spaces that we are going to consider, maybe let's just have a look at the existence theorem. The solution spaces will therefore be spaces with time. So the time so the x interval plays the role of a time interval in these Bochner spaces. And this space here covers the smoothness in y direction. And then one can show a certain existence and regularity with respect to these Bochner spaces. One can actually even do so with Q that not only depend on X, but also on Y. So let me show this here. So this DQ is a space of functions that depend on X. So 0, 1 is always the X interval. Certain summability. So for example, P equal to infinity would be a particular case here, but also P equal to 2 is something which we can do. And then we have a certain smoothness with respect to the perpendicular direction. So in our inverse problems that we consider, it was just constant in the other direction, but we can also admit certain variability in the other direction, smooth variability. As a matter of fact, what we would like to have is sufficient smoothness such that this H sigma space that we use here embeds into L infinity. And also we have a certain Banach algebra property in the sense that if you multiply two such functions, they are again in this H sigma space. Okay, that's basically the existence theorem. And let me just mention, because I showed it in the reconstructions that we used Newton's method to do our reconstructions. And for this purpose, actually, we can even do this with a Q that depends on X and Y. We will not uniquely recover the Q, but we can still apply Newton's method, and we can actually show that Newton's method converges. This is not so trivial for inverse problems, because actually one has to consider regularized versions of Newton's methods, such as this one here. So this is a regularization parameter, this gamma n here. So this is a regularization term. This is needed because the problem is ill-posed, as you have seen from the singular value decay. Also the linear problem, that's actually where we saw the singular values. So the linear problem is ill-posed. So recovering the Newton step from this part here needs regularization. That's done, for example, by Tikhonov. We also have another term here, since we actually want to recover Q that depends only on X. But we extend, in order to really get convergence of Newton's method, we extend Q to be an X and Y dependent function. In order to, after all, get uniqueness, we penalize Y dependence. So our Q in the course of the Newton method, we take it as close as possible to its mean value with respect to Y. Then with this choice of regularization parameters, so first of all, regularization parameters should tend to 0, but not too fast. That's this condition. And then we also have to stop Newton's method in order to prevent that the noise that is indicated here in the data, that this does not explode. So on one hand, we should iterate long enough. So as delta, as the noise level tends to 0, the iteration index should get larger. But on the other hand, this quotient should also be always stay bounded and even tend to 0 as delta tends to 0. And under these conditions, one can get convergence of this Newton type method as it's written up here. And with this, I would like to thank you very much for your attention.